Um, all right, guys. I was asked about putting together a little something about PES and kind of what it is to give you some background. So hopefully I can keep this to a short amount of time and not ramble. But this is something that I just threw together, and I'm calling it PES stuff because that's what I got. Our basic outline is that it takes energy to knock off an electron. And that energy is quantized. This is where we get some of our quantum mechanic thinking into stuff. And don't worry if the quantum is a little weird right now. We're going to get there. But with the PES, what we really do is we measure, we charge up a photon with a certain amount of energy, and then we whack it at a mole of atoms, and we see if it's knocking off electrons. So usually this is done on a per mole basis because that's something measurable that we can do. And then we graph it and we look at patterns. And this is how science works. You do some things, you look for patterns, you make some assumptions, and try varying it a little bit. So we've got hydrogen and helium, lithium, beryllium. No, I'm kidding. We don't have to sing the song. But you will notice that A, it's a log scale on the bottom. B, that first ionization energy for the only ionization for energy for hydrogen is 1.31. That's megajoules a mole. When we do helium, the peak grows, so there are 2 electrons there. The height is noticeably different, but it's also increased the megajoules per mole. And so as we do this, look at that increase. It takes way more energy to knock off those lithium electrons that are inside, but this outside one, it's sitting out here and can get whacked off fairly easily. What about now? Oh, that went up. That number went up also. So we do start thinking, this is according to Coulomb's law, if you have more protons, they're pulling harder on them, no matter how many electrons you get. Because the electrons, especially when you're knocking off the inside ones, all the other electrons are gone now. So they're just dealing with once you put this much energy in, you knock off the outside guys for beryllium, the inside guys are shielded. But when those are gone, they're just sucked close to the protons. So we do get these patterns that emerge. And there was the question about what the SP and D mean as we go in. So here's our first p orbit electron coming in with boron, and you look, yep, numbers are getting bigger. Now it does take a little bit less energy to knock off that first boron electron, but then you got way more on the inside. So it's going to take a combined giant amount of energy as you go from beryllium to boron to knock them all off. And these quantized values, these are just, they are quantum. That is a number that does not change. There's no half steps involved. These numbers don't seem to mathematically relate to each other very well at all. And it's just the way atoms are. But how the arrangement of the electrons look, don't worry about the math, but holy cow, look at that guy. Every electron has 3 quantum numbers, 1, 2, 3, and they represent place and direction of spin and other things. And this is just with hydrogen. So we made some probability density plots, like where is it likely to find that electron? And so with your S orbit, you've got the probability really right in there and a little diffuse probability out here, but there's nothing in the middle. That's the weird thing about these. They really do exclude a lot of area. You got your next set of electrons, and you got the middle, you got the outside, and this way outside ring where you might be able to find it. When you start doing p electrons, they tend to go one direction or another. These will actually be flipping, so you get it here and here, or here and here, depending on which electron it is. And you get the flips in a bunch of different directions. So these should be mirrored that way as we go through. This is trying to give you a 3-dimensional view of things, but it doesn't really work. And this looks bonkers. Don't worry about this too much. I just wanted to show you because the probability density plots are fun. This is the orbits set up kind of like the periodic table. So you got 1s, and then you got 2s. So you got a little thing in there. 2p, 1, or well, the x-axis, y-axis, and z-axis are sorry, Y, Z, X. I did that totally backwards, and the way that they fill up. And you will notice that when we get to the next level, you have 1, 2, 3 shells, and then you can't see it because it's blocked in here, but you have your, little guys in there. And so these are much larger than they were. And then we start filling in. And this is not a perfect representation of the periodic table because there are two 1s spots and two 2s spots. That's where you get that stair step going on. And it kind of looks like this. And it is a fair thing to say that on the periodic table, we might actually want to put helium all the way over next to hydrogen, so it lines up here, except helium also displays a lot of noble gas properties, so they stick it over here. It's a little bit of an outlier. But otherwise, the filling is going to follow. You've got your 1s's, and they fill up. You get your 2s's, and they fill up. And then we've got our p orbitals. You got to fill up your 2p's in there. And then we've got our 3s's, and then our 3p's that fill up. So you're kind of filling in order, and then 4s's, and then 3d. Wait a second. What is up with this? It turns out that when you are looking at the amount of energy, and this is just kind of a relative scale, the 1s is kind of low, 2s is higher, and then the 2p's are kind of, that seems like a half step higher right there. Same thing with 3s, 3p's, then the 3d's are up pretty high right there. And what gets me is the 3D is actually in between the 4s and the 4p amount of energy. If I draw myself a straight line, I can get it like, bam, right there. It is right in between. And after this part of the transition block, it all starts falling apart. So we don't worry too much about it. We just know that it's a little wonky. And in AP Chem, we're not really getting into anything else in a way that we care about electrons and their configuration. So we acknowledge it's a thing and we move on. Now, as we're going here, what else can we glean from our PES graphs? We've got the 1s, the 2s, the 2p, and you can count. You've got number of electrons, 1, 2, 3, 4, 5, 6. Sweet, carbon is element 6. You get one more 7, that's nitrogen, and you're going to see a slow march to the left, especially of this inside guy. Now, what you do get is sometimes the number here doesn't always shift to the left. So going from carbon is 1.09, then 1.4, nitrogen's got a bigger handle on it, then 1.31, that's not as big, and oxygen. And when you get here, then it gets bigger again. So there are some weird things. And this is where we get another idea. At the 3p position, or the P3, the third P of any shell, each of those electrons are filling 1, 2, 3. Then the next one gets doubled up into a spot with the first electron. So you've got 3 spots, and each spot has room for 2 electrons. Think maybe bunk beds. And just when you've got one guy doubled up, he's easier to kick out because the electrons do repel each other. When you add 2 guys doubled up, that effect is then negated by the extra pull of the protons, which I'm putting way over here just in my head. I know the protons don't exist here on the graph, but that's what it looks like it does. And I should say every once in a while you get these flipped in directions, so do kind of look, make sure it's going from lowest to highest in kind of the reverse way, because then when we read it, we read inside electrons first and we go to the outside electrons at the end. But you do get some changes. And then we'll go all the way up to 6. This is neon, it's noble gas, it's completely full up. And then we're going to add another shell. Bam! Oh no, wait, sorry. I set this up for you guys. So who am I? Identifying by the PES is a thing. And in this, you don't need any of the energy information. All you have to do is count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13, 14. So element 14, you'd have to go to a periodic table and look. And I would even double count me because I was singing along. 4, 5, 6, 7, 8, 9, 10. Good. 11, 12, 13, 14. I didn't count any of the zeros. Excellent. So it's element 14. And nobody expects you to know this off the top of your head, but you get out your periodic table, you count on your hands, and you find it. I'm actually not giving you the answer. You're going to have to find it for yourself. And then we've got this one as well. This is, looks like a lot, right? So we know that we've got 2 and then up to 10 in here. So then 11, 12, 13, 14, 15, 16, 17, element 17. Well, and I'm looking at it and I know that if it went up to that 6, that would be a full row and it would be another noble gas. We're looking for a guy 1 off of a noble gas. And it's in the 1, 2, 3 in the 3rd period. So this is hydrogen and helium. And this starts with lithium and goes all the way to, what is the first noble gas? Is that neon? You guys are going to have to find out. But this one is whatever's next to that second real noble gas, since I'm dissing helium over here. And you just get them counted that way. And there will, in all likelihood, be something that asks about this on the AP exam. They do like to have some PES questions. So you want to learn it, but don't spend a lot of time obsessing about it because we've got so much more to cover. And the basic structure of the periodic table and what that means about the inside of the atoms and how they work is really the point here. So I hope you learned something. If you have more questions, let me know and I'll try to give you some more answers. And until then, have a great day.